we are now on our second podcast about the concepts of modern physics. Good day, Rai.
Good day, Odessa, and to all watching this podcast. In this video, we are going to talk about the rest of energy, total energy, specifically the relativistic total energy, and the relativistic energy itself.
That's right, Rai. And just like the first podcast, we will impart our learning and understanding of the said topic.
That's right. So let's get started. I guess you'll be the one to spill the tea first, Odessa.
Alright then. Well, rest energy, I believe it is equivalent to the mass of an object. With Einstein's famous formula, the EmC squared, rest energy of an object is given by the rest energy is equal to the product of mass of an object and speed of light squared. It is basically associated with the mass of the object since the volume of the speed of light is constant, that is approximately 3 times 10 raised to the power of 8 meter per second. Simply, we consider mass here as a form of energy, but when the energy is stored in the object, the rest mass increases because the mass itself increases as energy is stored in it. And in order to release energy, the mass will be destroyed.
That's right. Based also on how I understand this topic, the Einstein Equation includes both the kinetic energy of a particle and the energy it has as a result of its mass. If the particle is at rest, then the energy is expressed as what have you said, E is equal to mc squared, where E is the rest energy, m is the mass, and c is the speed of light squared. The formula shows that energy is related to the mass of an object at rest. For instance, if energy is stored in the object, its rest mass increases. This implies that mass can be destroyed to release energy.
Yes, that's right. We've been saying this since the first podcast that we have different ways of understanding modern physics topic like this, yet we still end up with the same thoughts. By the way, what was just Rai and me have shared was just one of the first concept of the two equations relevant to relativistic energy.
Indeed, the other one is the relativistic total energy. Total energy, as what have I understood, can be defined through the formula E is equal to lambda mc squared, where m again is the mass, c is the speed of light, and v is the velocity of the mass relative to an observer. The total energy includes kinetic and potential energy, and it is related to relativistic momentum. We only have to remember that at rest, total energy is not zero. Rather, v or velocity is equal to 0 when lambda is equal to 1. That is the time we consider that the object has the rest energy.
Thank you for that, Rai. By the way, relativistic energy includes the possibility of mass to turn into energy for it to be conserved. Okay, so the total energy, based on how I understand it, is determined as the sum of the rest energy and kinetic energy. Why is this so? This is because we assume that the object's potential energy is 0. There comes when the object is moving, then we take into account the object's kinetic energy to find the object's total energy. Kinetic energy in classical physics is given by 1/2 times mass times the square of the speed or the velocity of the mass. To find the relativistic total energy, we use the formula E is equal to the quotient of mass times the speed of light and the square root of 1 minus speed of the object squared over speed of the light squared. While finding the relativistic kinetic energy, we use the formula kinetic energy is equal to the product of mass times the speed of light squared and the difference of 1 over the square root of 1 minus speed of the object squared over speed of light squared and 1. We come up to this formula as we mathematically manipulate the formula in getting the kinetic energy, which is the difference of the total energy and the rest energy. We just substitute the formulas in getting the relativistic total energy and rest energy. To sum it all, the rest energy is associated with mass of the object, and we consider mass here as a form of energy that is determined using Einstein's famous equation. Next, energy is conserved so long as the possibility of the mass mass changing to energy exists. Third, the relativistic total energy of the body on the Lorentz formula times the rest energy.
Well said, Adessa. The first postulate of relativity states that the laws of physics are the same in all inertial frames. Einstein showed that the law of conservation of energy of a particle is valid relativistically, but for energy expressed in terms of velocity and mass in a way consistent with relativity. Consider the first relativistic expression for the kinetic energy. We again use the velocity to distinguish it from relative velocity between observers. Classically, kinetic energy is related to mass and speed by the familiar expression kinetic energy is equal to 1/2 times mass times velocity squared. The corresponding relativistic expression for kinetic energy can be obtained from the work energy theorem. This theorem states that the net work on a system goes into kinetic energy. Meanwhile, the second postulate is the idea that the speed of light is constant, independent of the relative motion of the source. Here is where the ultimate speed of light enters, stating that no object with mass can attain the speed of light.
Thank you, Rai. I guess this is where our second vodcast ends. I really have a great time. Also, I've learned a lot.
Me too, and I'm hoping that they have learned a lot too while watching us. Thank you, everyone. See you on our third vodcast.